This is Navneet Krishnan from iitiansgateclasses. In this section, we'll be seeing GATE 2022 Aerospace Engineering Flight Mechanics Part Detailed Solutions. There have been total question asked in flight mechanics is 8 questions, out of which 1 mark question is 2, 2 mark question is 6. So total marks asked in flight mechanics is 14 marks. GATE 2022 question number 18. The service ceiling of an airplane is the altitude at which rate of climb is 100 meter per minute, beyond which theoretically the airplane cannot sustain level flight. Option C is at which maximum power is required for the flight. Option D is maximum rate of climb is 100 feet per minute. If you take piston engine aircraft, for piston engine aircraft alone, rate of climb is the altitude at which the service ceiling is the altitude at which rate of climb is 100 feet per minute. Same way for jet engine aircraft, it is 500 feet per minute is the rate of climb corresponding to service ceiling altitude. Now, if you see, they have not mentioned anything regarding piston engine or jet engine aircraft. So, option D cannot be correct. And first, option A is wrong because it doesn't correspond to any of this. Second, option B, beyond which theoretically airplane cannot sustain level flight. It is corresponding to aerodynamic ceiling. It is not a aerodynamic ceiling or absolute ceiling altitude. It corresponds to absolute ceiling or aerodynamic ceiling. So it is not the definition of service ceiling. Service ceiling is the altitude at which you require the maximum power required for the flight. Theoretically, possibly, maximum power required flight. Because beyond service ceiling, it is not theoretically possible to reach absolute ceiling, because to reach absolute ceiling, it takes infinite time. So theoretically possible maximum altitude is service ceiling, at which power required is maximum for the flight. So option C is the correct answer, because as altitude increases, power required keeps on increases. Service ceiling is the maximum altitude theoretically possible to achieve. So that means that is the altitude at which power required will be maximum. So option C is correct. Next, question number 19. Regarding the horizontal tail of a conventional plane, which one of the following statements is true? Option A, it contributes to Cm alpha less than 0. Option B, it makes Cm alpha equal to 0. It makes Cm alpha greater than 0. It makes Cm not greater than 0 and Cm alpha greater than 0. See, I'll eliminate one by one option. See, Cm alpha equal to 0 corresponds to neutral stability. Okay. Yeah, for previous question, C is the correct answer. For this question, option B is wrong. Why? Because it doesn't correspond to neutral stability. It not only makes the airplane to be neutrally stable, it makes the airplane to be stable. Okay, horizontal tail is the component which brings aircraft stability. See, if you take wing alone configuration, Cm naught or Cmac is negative. Cm alpha is greater than 0. What happens when we add HT? HT only makes Cm naught greater than 0. That is, it brings the airplane to equilibrium and balance. That is, HT makes the airplane to bring that to equilibrium and balance. Okay. Next one is Cm alpha less than 0. By because longitudinal stability, dou Cm by dou alpha should be less than 0, which is brought by horizontal tail only. So option A is correct. It contributes to Cm alpha less than 0. Option C is wrong. Why? Because wing only contributes Cm alpha greater than 0. But horizontal tail makes the airplane Cm alpha less than 0 in order to bring horizontal stability. This one, Cm not greater than 0. Yes, horizontal tail brings Cm not greater than 0. But Cm alpha less than 0 means option D would have been correct. But it doesn't, because it is corresponding to unstable configuration. HT will not make the airplane unstable. It brings the airplane to be stable condition. So only option correct is option A. Okay. Next, question number 27. For international standard atmosphere up to 11 kilometer altitude, which of the following statements is true? If you see, up to 11 kilometer means it corresponds to tropopause, that is troposphere. If you see in troposphere, for deriving the relation for troposphere, we would have used hydrostatic equation, that is dP equal to minus rho g dH. So for calculating atmospheric properties, we use hydrostatic equation. From that only we derive that relation. So option A is correct. Next, temperature lapse rate is taken as in troposphere. The lapse rate for lapse rate is minus 0.0065 Kelvin per meter. So option B is wrong. Now if you say option C, sea level atmospheric conditions are 1.01325 into 10 power 5 Pascal is the pressure. Density is 1.225 kilogram per meter cube. But sea level temperature is not 300 Kelvin. It is sea level temperature is 288.16 Kelvin. So option C is also wrong. Next, option D. Air is treated as a perfect gas. Yeah, air is treated as a perfect gas because we use ideal gas equation PV equal to MRT in order to derive all our relations in troposphere. From this only we make sure that the relation between pressure and the density is maintained. That is mass by volume with density rho RT. So air is treated as only perfect gas. So option A and D are true. Option B and C are false. Okay. Next. Question number 32. An unpowered glider is flying at a glide angle of 10 degree. Its lift to drag ratio is dash, round off to 2 decimal places. So for a gliding flight, tan gamma is given as h by range, that is equal to 1 by L by T. For all gliding flights, this is the equation. So what happens? L by D is nothing but 1 inverse of tan gamma. Gamma is 10 degree. When we substitute gamma equal to 10 degree, I get the value as 5.671. So if we round up to 2 decimal places, it is 5.67. Okay. Next, question number 40. Consider a conventional subsonic fixed wing airplane. E is the Oswald efficiency factor and AR is the aspect ratio. Corresponding to minimum CD by CL power 3 by 2, which is the following relation is true. See, minimum CD by CL power 3 by 2, which means maximum CL power 3 by 2 by CD, which is corresponding to minimum power required condition. Minimum power required condition. Minimum power condition is nothing but CD naught equal to 1 by 3 CDI. So CD naught equal to 1 by 3. CDI is nothing but KCL square, where K is nothing but 1 divided by pi EAR into CL square. This is your CD naught. So from which CL square can be written as 3. If I take this on the other side, it becomes 3 CD naught pi EAR. Okay. So what is CD? CD is nothing but CD naught plus KCL square. So KCL square from this relation can be written as 3 CD naught. KCL square can be written as 3 CD naught. So CD naught plus 3 CD naught, which means 4 CD naught. CD by CL square, that's what they require. CD by CL square is 4 CD naught. CD is 4 CD naught. CL square is 3 CD naught into pi AR. So CD naught is cancelled. So it is 4 by 3 pi AR. Okay. So option B is the correct answer. Option B is the correct answer. Okay. Next. Question number 45. For a conventional airplane in straight level constant velocity flight condition, which of the following conditions are possible on Euler angles pi, theta and side angle of attack and side slip angle beta? Now if you see, constant velocity means it is steady flight. Constant velocity means it is steady flight. Steady, straight and level flight conditions. That's what they have asked. So if you see, pi corresponds to roll angle. Pi corresponds to roll angle. For a steady level flight, roll angle should be 0. Then only you can achieve steady level flight. Psi corresponds to yaw angle. When there is a steady level flight, yaw also should not take place. So yaw angle also should be equal to 0. When there is a beta equal to 0, beta is corresponding to side slip angle. When there is a side slip, what happens? The airplane moves sideways, so it corresponds to yaw, and which will, due to cross coupling effects, it will undertake a roll also. So side slip should be also 0. Only way possible is angle of attack can be any angle, 2 degree or 5 degree, any angle it is, or 3 degree, whatever. Here the angle of attack is mentioned is 2 degree and 3 degree. It is possible. Angle of attack 2 degree and 3 degree is possible. Corresponding to that, pitch angle is nothing but alpha plus climb angle gamma. So if it is 2 degree, angle of attack is 2 degree and theta also 2 degree, which means that climb angle gamma is equal to 0. Because in this first option A, if you take theta equal to 3 degree and alpha is also 2 degree, which means alpha 2 degree, theta 2 degree, which means gamma is equal to 0. That is climb angle is 0. So in a steady level flight, there should be 0 climb. So climb angle should be 0. So option A is correct. Okay. Option B, why it can't be correct is, it is having a climb angle, it is having a roll angle 5 degree. So roll is not possible in a steady level flight. So option B is wrong. If you take option C, there is a side slip of 5 degree. So option C is also wrong. For a steady level flight, so there should be 0 side slip. Then option D, if you take this, there is a beta is also 5 degrees. So this cannot be happening in steady level flight. And one more thing is, if you take theta equal to 5 degree, alpha equal to 2 degree, gamma is nothing but theta minus alpha, which is 5 minus 2, which is 3 degree. So there is a climb taking place. In a steady level flight, climb cannot take place. So option D is also wrong. So only option correct is option A. Next, question number 54. Question number 54. Consider a thin symmetrical airfoil at 2-degree angle of attack in a uniform flow where velocity is equal to 50 meters per second. The pitching moment coefficient about its leading edge is dash. Round off to 3 decimal places. Pitching moment coefficient about leading edge. This is corresponding to thin airfoil theory. Okay, this is corresponding to thin airfoil theory. Pitching moment coefficient about leading edge according to thin airfoil theory is given as CMLE is nothing but minus pi by 2 alpha, where alpha is in radians, or minus CL by 4. Since angle of attack is given, angle of attack is 2 degree. But we have to convert into radians in order to use this relation. So if I have to convert 2 degree into radians, multiply it by pi by 180. So CMLE is nothing but minus pi square by 180, which is nothing but minus 0.0548. Round off to 3 decimal places means 0.055. CM, pitching moment coefficient about leading edge, is minus 0.055. Conventional airplane. A conventional airplane of mass 500 5000 kg is doing a level turn of radius 500 1000 meter at a constant speed of 100 meter per second at sea level. Take the acceleration due to gravity as 10 meter per second square. The banking angle of this airplane is dash degrees. What they given? They given radius of turn, level turn. For level turn flight, the radius of turn is nothing but r equal to v square by g into root of n square minus 1. Radius of turn we know it is 1000 meter. It is given. Turn radius is speed is also given 100 meter per second. Acceleration due to gravity is also given, which is 10 meter per second square. They asked us to take 10 meter per second square divided by root of n square minus 1. So if I take root of n square minus 1, if I take 1000 this side and root of n square minus 1 that side, it will become 100 square by 10 into 1000. So this is nothing but 1. Square on both sides. When I square on both sides, it will become n square minus 1 equal to 1. Take this 1 on the other side, n square equal to 2. N equal to root of 2, which is nothing but 1.414. N is nothing but secant pi. Secant pi is equal to root of 2, okay, which means inverse of cos pi, that is equal to root of 2. So cos pi is nothing but 1 by root. So pi is cos inverse of 1 by root 2, which is nothing but 45 degree. So 45 degree is the banking angle. With this, all the problems of GATE 2022 of flight mechanics is solved. Any doubts? First option, CD equal to KCL square. CD equal to KCL square. That is, one second. First, CD naught equal to CDI, corresponding to minimum drag condition. Minimum drag condition, which is TL by CD max. So for that, CD is nothing but CD naught plus KCL square. So CD is nothing but that is CD naught equal to KCL square. That means CD is 2 CD naught. So other one is CD naught equal to KCL square, from which KCL K is nothing but pi AR into CL square. So CL square is pi AR CD naught. So if I put that CD by CL square, 2 CD naught by pi AR. If it is minimum drag condition, we have to derive like this only for CD by CL square. But here 1 by pi AR, CD equal to pi AR, KCL square unknown. Here if we take CD equal to CD naught plus KCL square, in which K is nothing but 1 divided by pi AR. So CD naught is missing. So parasite, zero parasite drag. When you have zero parasite drag only, CD by K is nothing but CD by CL square is nothing but 1 divided by pi AR. If we have zero parasite drag only, CD can be equal to KCL square, where K is 1 by pi AR. So CD divided by CL square can become 1 by pi AR. So if there is only zero parasite drag only, this relation holds good. Zero parasite drag only, this relation holds good. This doesn't have any meaning at all, because CD is okay. We'll derive this also. So which means that this is also not having any relation, because CD is nothing but KCL square. CD is not only dependent on CL, it is dependent upon KCL square of it. So here this relation also doesn't hold good, because it doesn't have a direct relation between CD and CL. Okay. This one, if you see, if CL square, CD divided by root of CL. So if I put beneath root also, it will become CL. That is equal to 1 by root of pi AR. In zero parasite drag condition, CD by CL is nothing but 1 by root of pi AR. It is not corresponding to any other conditions. So this is also wrong. Only option correct is option B, which is corresponding to minimum power required condition, that is CD by CL square, CL power 3 by 2 minimum condition, corresponding to that, which is CL power 3 by 2 by CD max condition. Okay.